We know that the world is really continuous time, at least as far as we're concerned. In our, when you're walking down the street, we've sort of been, we inherently sort of think of, things like velocity as continuous functions. So if we could plot velocity sort of like this, who knows, right? And because it's a continuous time function, I could go in and say, what's the velocity at 1.01 seconds, right? Or what is the velocity at 1.0001 seconds? We have this sort of freedom when thinking about the world in continuous time where t can be anything, right? It could be 1, it could be 1.01. We don't know. Digital systems don't have that freedom. They're way more constrained. They only view the world and think about the world in discrete measurements, and that's a big difference. Okay, so for those calculus people out there, derivatives and integrals, as you've learned them, they don't, while the ideas underneath are still really relevant, they're not implemented the exact same way. And so how can we think about the world in discrete time? Right? If you are only measuring the world at certain points, spaced out by our sample time, how do we do everything, right? We don't have these calculus tools. All we have are measurements of, let's say, velocity here, 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 here. How can we work with them? And in situations where you don't have to care about past measurements, so let's say we wanted to do the brightness of an LED at some point in time. We were assigning that in our code, and we were going to say that was based off of some gain k, some number, who cares? Maybe it's 5, times our velocity at a certain point in time. If we wanted to do this in code, we can, and it's totally easy. Maybe it would be just one line. We don't have to worry about the past or anything like that. And this isn't too hard to think about. Now what gets tricky with discrete time and where we need to start making some assumptions, however, is what do we do whenever we want to be making decisions based not on things in the moment, but maybe things over time. And so we could come up with a list of them, right? So if you have velocity, we want to go to maybe position, we need to make some assumptions about what the real life velocity was. Same thing like if you have acceleration right here, and we want to go to velocity, or figure it out, or come up with an expression for it. We need to also make assumptions. By assumptions, I mean if all you know about the world is that the velocity was this value, and then this value, and then this value, and then on, how could we reconcile what the digital system thinks the world is doing? So there's been some discussion in the forums about why do we come up with something like, let's say we have a position d of n, and so this is the position of a robot or a cat, I don't know, at time point n. Why do we say it's going to be based off of this expression? Right? Some people have suggested, and it's totally fair to do that, you could also have done right? This is an alternative, right? We're saying, so in the top one, we're saying that our distance at a time point n is going to be based off of our previous distance plus time times the previous velocity. While here we're saying our distance is based off of our previous distance plus time times the current velocity. Now both of these are actually valid. Like neither of them is better than the other in some sense. What this top one is saying, it's sort of making the assumption that our system's getting measurements of velocity every time step, right? And what the top one is saying is from the measurement point to the next time step, it stays at the measurement point value. So it's going to it looks like this graphically. So we carry forward in time the value of a time step. While this one right here is doing the following. So if our values are like this, our discrete time values, This one is sort of graphically doing this. Okay, and they are different, right? So let's say that, our honest, like the actual continuous time behavior of the system looks like this. All right, I'm just filling in the dots here. And again, I should label my axes. Apologies. N, N. So this would be V of N. This is V of N. And so you can see there's two different things going on here, right? In the top one right here, and so when we make that measurement, it carries forward. While here, the measurement actually carries backwards. Now, which one's right? It actually, both are right and wrong. They're both wrong in the sense that they're discrete approximations of what's really happening in real life, right? Like, in real life, it's continuous time. It's actually this green line, this lime green line right here. But in discrete time, we're limited. We do not have every data point, right? We can't say what is the velocity at time step 1.03, right? That doesn't make any sense. We can only have integer number of time steps, right? And so in both the top and the bottom versions of this difference equation, we are wrong in a sense. But they're also both right. Like, they're both perfectly legitimate assumptions to make, right? In the top one, we're saying that when I have a velocity measurement, I'm assuming the system's velocity stays the same until the next time step. While in the bottom one, we're saying when I have a velocity measurement, I'm assuming that velocity was what had previously existed over the last time step duration. So it's a slight minor difference. What we're going to do in our class, and we're just going to pick one because it makes our handling difference equations a bit easier, is pick the top one. Like this, okay? The important thing to keep in mind, too, is that as time gets really small, so like let's say we actually had a continuous time function, and it's maybe green, whatever, right? As you go to very, 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 very small time steps, all right, and we're taking all these measurements, and then if we do, this forward or backwards approximation that we're doing, right? Actually, as you take them very, very, very small, what you'll see is they actually approach the same thing. And the smaller we go, the smaller our time step, the less and less the error is, and the less that this decision we're making really matters.